Thank you very much, everyone, for joining us today for our Vaegan seminar, which will be presented by Dr. Stuart Anstis, who completed his PhD at Cambridge under the supervision of Professor Richard Gregory. He taught at the University of Bristol in the United Kingdom and at York University in Toronto, Canada. Since the early 90s, he has taught at the University of California, San Diego, and has been a visiting scientist to other institutions, including the Smith-Kettlewell Institute and the San Francisco Exploratorium, as well as the IPRI in Japan, which I believe is a government science organization. He has published more than 120 papers on perception, with topics ranging from things as diverse as visual artifacts through to the apparent size of holes felt with the tongue. He has given over 250 invited presentations on his research throughout the United States, Europe, and Japan, including an invited address at the President's Symposium at the annual meeting of the Society for Neurosciences. He also gave the 1998 Max Wertheimer Lecture in Frankfurt. His work has featured in magazines and occasionally appears on television programs. I believe you even appeared yourself on the Shirley Solomon Show. Do you recall that?
Yes.
Speaking about eccentrics. He has won awards as an outstanding teacher at York University and UC San Diego. He's a Humboldt Fellow, a visiting fellow at Pembroke College, Oxford, and a recipient of the Kurt Kofka Medal for outstanding contributions to vision science. He now lives in Del Mar, California, where he's currently sitting. And thank you so much, Stuart, for joining with us today. And welcome to your UNSW Vaegan seminar.
Thank you very much, Juno. Here is talk number 251. I've been working on interaction between motion and position together with Patrick Kavanagh, FRSC. He's a fellow at the Royal Society of Canada. Now, I should mention that when I change my slides, you've got to change yours. I can't do it for you. So I hope we stay in step. So as I was saying, every time I hit the left or right arrow button, I'll make a little click. I'll try again. And that means do the same thing, okay? And if we really get lost, I'll call up the number of the slide, which is written bottom right of each slide, okay? Let's go. A click, that was. No, let's try again. Click, click, click. Oh, okay. Okay, the human brain has got two channels, one for what and one for where. And we use the where channel to tell us where we are in space, but more important, where objects are in space. And it turns out that the receptive field location is a basic property of each visual neuron. And these are organized into retinotopic maps throughout the visual system. So is visual location coded as retinotopic location inside the brain? Isn't that the code? Well, probably not, because if you see these vertical red and green bars, they flash out. They're always vertical, but when we put wheels behind them that are rotating, the bars themselves seem to be tilted. The red bars seem to tilt in and the green bars seem to tilt out. Though, of course, they are always, as you can see, vertical. And we call this the flash grab effect. And that's what we'll be talking about this afternoon. Okay. Now, as a mnemonic, which way do you see the apparent shift of the flash targets? Well, the targets get apparently drifted along in the direction in which the background moves after, not before, the target flashes. So the target flashes, and then there's motion behind it, so it gets dragged along after the flash. And we'll see later, this is consistent with an apparent shortening of the background motion. We'll get back to that later on. Here's another example. These red and green spots flash, and they're always in the same locations. But now when we have a rotating annulus, the green spot seems to be shifted from noon round to 11 o'clock, and the upper red spot shifted from noon round to 1 o'clock. But you can see they really are in the same position. I'll give you one more look at that. Okay, those red and green bars, spots actually in the same position. Here's another example for you. Now, this cannot be due to eye movements because these annually rotate in opposite directions. So you get two opposite flash grab effects. And no one can move their eyes in opposite directions at once. So it can't be eye movements. Now, it doesn't have to be spots. We get the same thing for big cross. You'll notice this big red cross flashes, well, between red and green, but the red and green are always in exactly the same position. But now we turn on a rotating wheel background, and you see that's going to drag the cross around. It's hard to believe those verticals are still vertical, but they really are. You notice also the cross is all bent out of shape. We call this a wonky cross. And the reason is the verticals get bent out more than the horizontals because you notice the verticals are flashed up on the edges of the moving sectors of the wheel, which gives a lot of pulling power, whereas the horizontals fall in the middle of the sectors, which do less pulling. That's why the bending is non-uniform. Here's another wonky cross case. Sorry, next slide. It's hard to believe that the red and blue crosses are superimposed and identical. They're still right angles, but they are. The moving lines somehow drag them away from their positions. And we're now on slide 11. Let's go on, click. Now slide 12. Now this time, those flashing targets are actually moving slightly, but they're both moving to the same amount. But the target on the right is on the background of a wheel that moves very little, so it shows very little movement. On the other hand, the target on the left is on a wheel that's making a very big movement, so the left-hand target seems to move through a big distance. So this shows that the background movement has a strong influence on the apparent target movement. Click. So we call this a flash grab effect. And what we find is that when the background square moves left and right, the target, which is flashed at the turnaround point of the square's motion, seems to jump in the opposite direction. Here's some examples. Now you're going to see a red and blue spot, which always superimpose flashing in the middle of the screen. But when the square, you can see that now, they're both superimposed. But when we turn the square on, and that moves from side to side, it seems to drag the two spots apart. So now the blue spot looks way over to the left of the red spot, though they are actually superimposed on the screen. And they look separated by, oh, I'd say 3/4 of the width of the square. So it's really quite a big effect. In fact, you're probably thinking, well, this sounds just like induced movement, but it's not. It's much stronger than that. You can see now that when the target is stationary, it's rock solid. It does not seem to move. And this is what Dunker used. Okay, now on slide 16. Now, in a moment, in the left-hand window, you're going to see a spot jumping up and down, but not through a vertical axis, along an axis tilted 42 degrees away from the vertical. But then we're going to turn on a moving square, and that will null this out so that the motion of the target will look vertical, okay? So that means we have a 42 degrees illusion, which we can null out with a flashing target. On the right in a moment, we'll have the same thing, but now the target will be just continuously moving up and down. So let's see the first one. Click. Okay, you should see the spot fixed in position. And in a moment, okay, the other square comes on. And now it looks as though that spot's moving up and down vertically. Do you agree? Okay, click again. And now on the right, we see a spot moving continuously, but it's tilted only 20 degrees away from the vertical. And now the square will gradually fade up, and that will now null out the effect. So the spot that's really moving at 20 degrees appears to be vertical. Now compare the two windows. On the left, the flashing spots which are tilted 42 degrees get nulled out. On the right, the continuously moving spot is tilted only 20 degrees. So this shows the flash grab effect is twice as big for a flash target as for a continuously moving one. And we've, of course, used flash targets throughout. The motion on the right may appear vertical, but the motion path actually moves left and right. Okay, click again to slide 17. Now, this flash grab effect is not local. Okay, you see now the flashed spots actually superimposed, but they look shifted. The blue spot looks shifted to the left. And it still looks shifted even when we change the size of the square. Even when it's so small, it seems to lie between the two spot positions. In other words, this is a very robust illusion, and the flash grab does not depend upon the spots being near to the moving contours. It looks like the square can be anywhere within the screen, and we still get quite a decent effect. Okay? And remember, those two flash spots are always superimposed, that they look separated. Click for the next slide. Now on slide 18. Well, how much frame do you need? Now, here we've got the flashed spot always in the same position. And instead of a square, we're going to use a bunch of dots now. And I think you get quite a good effect. It looks the blue spot is to the right of the left spot, of the red spot. They're actually superimposed. Now we're gradually peeling off the spots one by one to see how few spots can still give the effect. We started off with about a gazillion spots. Now we're down to 5 or 6, and you still get the effect. Even when you get down to only 2 spots, you still get quite a robust effect. 1 spot doesn't quite seem to do it. So the threshold to get a flash grab seems to be a single moving spot. We haven't quite decided why just 1 spot is powerful enough to move that flashing target as strongly as it does. It's just cycling again. Okay, we've seen that. Okay, I'm clicking on to frame 19. Now, instead of a scattered lot of bits, we're now going to have 2 frames nested. When you have just the outer spot frame moving up and down, the spot appears to jump up and down, though of course it's always stationary. But when we have the inner frame moving left and right, the spot also seems to move left and right. Now, as before, that target's always flashed stationary on the screen. And you see now the outer spot's frame will win when it's on its own, but the inner frame will predominate when it's there. And notice how the motion of the spot, which is illusory, changes from vertical now to horizontal here. Click on frame 20. Once it's slight, see if this is going to work. I rather doubt it. Yeah, didn't like it. Well, let's ignore that slide. It wasn't a very good one. See if I can make this work for you. Click. We're now on, there we go. Is that working for you? We now have, the target is now a square that's either red or blue, and the red and blue squares are identical. Same size, same position, same everything. We're now on slide 21. And at the top, you see the words, moving background massively distorts the shape of targets. Can you see that on your screens? In fact, it's such a strong effect, it's quite difficult to put your finger on, let's say, the red or the blue square. And what's true for square is also true for shapes. I'm going to click now to go to slide 22. And now, again, we've got a red and a blue square, which are superimposed and identical. But the background, which skews back and forth, turns those two congruent squares into apparent rhombuses, rhombi, parallelograms, tilting left and right. So the background can have a massive effect on the perceived shape, size, and position of a flashed target. Now, what kind of motion do you need to do the flash grab work? It turns out it's not raw motion that grabs the target. The motion has already been analyzed or interpreted before you get the flash grab effect. Here, the target on the left is a single black spot that flashes always in the same position. And on the right, another black spot that also flashes in the same position. Now, on the left, you see a tilted rectangle that slides up and down. And the spot is flashed at top and bottom of the square. And that appears, the target seems to jump up and down, okay? On the right, we have exactly the same rectangle moving up and down, but the horizontal slit provides a kind of barber pole effect So it looks as though the rectangle is just moving left and right. As a result, the flashed black spot also seems to move only left and right. So now compare the left and right flashed targets. They're actually both stationary, flashing in the same position. But the spot on the left seems to jump up and down to a large distance. The spot on the right seems to jump left and right to a small distance. That's because you somewhat interpret or analyze the motion of the tilting background before it applies a flash grab to the flashed targets. Now here's another way in which motion is interpreted before the flash grab is applied. It turns out the path taken by the moving square matters. Now so far, you've always seen a square that just slides left and right and you get a flash at the two endpoints. But it turns out it matters not only where the square is when the target's flashed, but what it's doing on the screen when the target's not there. Let me show you what I mean. Here we have, top and bottom, a flashed pink spot that always says just where it is. At the top, you still get a good flash grab effect. As the rectangle goes to the right, the target seems to place to the left and so on. Now, the spot also does a little hop, skip, and a jump as it moves left and right, but that doesn't matter. You still get a good effect. But at the bottom, the rectangle rotates, and now the flash grab is completely gone. You go on seeing that flashed target exactly where it is. But notice the positions of the rectangles are always the same when the targets are flashed. They are left, right, okay? So what matters is not just where the rectangle is when the flash comes on. Somehow you must interpret the motion in between to decide whether it's going to grab and carry the flashed target. Here's another example of interpreted motion. Okay, you see you have these three identical rectangles and three spots which also flash up. As before, each target, each black spot, flashes in the same position. It never moves. Now the top rectangle just slides back and forth and you get the usual flash grab effect. The spot seems to be left, right, as the rectangle goes right, left. But now the middle one, I call this an inchworm. And here you see that this rectangle squishes up before it expands again. And you'll notice it has the same end positions, left, right, as the upper rectangle, but there's absolutely no flash grab effect. The position of that flashed spot is rock steady. Similarly, the bottom rectangle, which I call a footworm, here it expands in size before it moves. So it changes its shape, like the opposite of the inchworm. And once again, the flashed spot shows zero flash grab effect. It's just rock steady. So this again confirms that the positions and the movements of the rectangle between the targets is analyzed before we decide whether to apply a flash grab or not. So our interim conclusions are that the moving frames, in this case moving squares, shift the perceived position of the flashed tests, the little spots. And these flash locations are experienced relative to their position in the frame, not relative to the whole screen or to the world. And yet the motion of the frame itself is almost ignored. So relativity seems to rule. Now we've shown you that the flash grab can shift the perceived position of objects as well as their shapes. I want to show you now it can make the position of the background flash targets uncertain. So you don't know quite where the flash targets are. And this is especially true for some older folks. Here you see two crosses, red and blue, and it looks as though the red cross is up to the left of the blue cross. In fact, as you'll have figured out by now, the two crosses are in exactly the same position on the screen, in the middle of the screen. It's just the moving square that seems to shift them around owing to the flash grab effect. We're now on slide 29, okay? Now what I did was I gave people a cursor, started on the edge of the screen. I said, please move the cursor as quickly as you can onto the blue cross. I didn't tell them the red and the blue cross are in the same position. Now, what are the results? Here they are. Now, what I did was I got about 50 people aged from 18 to 92, and I ran them on this test. Along the bottom, we have their ages, you can see from 18 to 52. Up the side, the time it took them in seconds to move the cursor onto the target. Now, I've used a log scale on the Y for no particular reason, just to squish the data in. I'm not making any theoretical claims. Now, look first at the left-hand half of that screen, are the people aged under 65. Each blue dot represents an individual, and the X position shows how old they were, the Y position, how long it took them to do the task. And you can see all these people under 65, it was a trivial task, took only a few seconds. Now look at the right half of the graph for the people over 65. For about 1/3 of them, that's the blue spots at the bottom, they were still equally fast, it was still a trivial task. But for the remainders, all those yellow spots, it didn't take a few seconds, it could take up to 2 minutes to get the cursor onto the target. Often they'd move the cursor over the general neighborhood and flail around. They just couldn't seem to know where the target was. They couldn't get the cursor onto it. And I'm afraid I am one of those yellow spots up there. I won't tell you which, but I'm certainly not 92. Now, what causes this effect? Is this problem a perceptual or a motor one? I'm almost sure it's not a motor, but a perceptual problem because of a controlled experiment we did. Top left, you can see a little, we're now on slide 31. Now, I'm going to click the thing again to make the little movie on the left work. The same movie you've seen before. We've got a cross flashing up in the same position, but a square moving around it gives it an illusory movement, so that cross appears to move up, left, and down, right. At the bottom, click again. Okay, we're still on slide 31, but that bottom movie, we now have a cross actually did jump back and forth, so at the same real distance as the illusory movement you saw just before. I took 5 of the slowest, oldest people to see how long it took them on this task. And oddly enough, when they're given the task shown at the bottom, where a cross really did move back and forth, they were very, very fast. Look at all the X values, all very small. Again, it took them only a few seconds. But when we gave them the task shown on the left, that's the Y-axis, you can see the Y values are very high. It took them a very long time to move the cursor onto the illusory motion, 4 or 5 times as long. So paradoxically, it took longer to move the cursor onto a stationary cross that seemed to move than it did onto a cross that actually did move. The reason why I have no idea, but maybe one day this will become a test of something or other, some kind of degeneration with age. Not that I believe there are any degeneration with age, but I'm funny that way. Okay. Excuse me. Sorry. Okay, so what causes this flash grab? We have 2 theories. Well, they might both be wrong. It's unlikely they're both right because they seem to contradict each other. The first theory is a local one, that you get perceived shortening of the paths of the moving squares. The second is a much more sophisticated cognitive theory based on Johansson's ideas of common versus differential motion. Let's look first at theory number 1 about apparent shortening. The idea is this: we've got rather limited bandwidth for processing motion, rather poor temporal resolution. So if you look at a moving spot, you probably average over time, so you convert its motion, you look at a sort of long sausage and amalgamate that into a single perceived position. And this temporal averaging shortens the paths of moving backgrounds by rounding off turnaround points. Let me show you what happens if you have a zigzag motion and you look at it with some sort of temporal integrating time. Well, first of all, look at these 2 vertical bars, and we're now on slide, I don't know where we are. These rotate back and forth through 180 degrees, so they're vertical, but somehow they don't seem to go through 180 degrees. Looks like about 170 degrees. So the red bars appear to tilt outwards and the blue bars tilt inwards. Here you can see your own perceptual shortening of the path length. Now let's see what we think might be happening. In this graph, time goes left to right and space goes up the page. Look at that zigzag line. That's the path taken by a moving square, okay? That's its physical motion path. Now that red rectangle is going to move along, and that represents an averaging time window which will apply to moving objects. If I click, maybe I can make that move along. Yes, it moves along, and you can probably see it converts that zigzag motion into a sine wave. And notice the sine wave has got the corners rounded off, so the amplitude of the motion is less perceptually than it is physically. So we think, therefore, when you see a square or a line moving back and forth, it's seen to move through a smaller distance than its real distance. The same is true for an object moving around the circle. Click, next slide. No, it didn't work. I'll try it again. Click, next slide. Okay, I can't see the slide numbers. Okay. Here you see a spot, which I painted green. This stands in for whatever you like, moving around the circle. It's followed by a black quadrant, and that's supposed to be the spatial extent of its like comet's tail, which gets averaged together in the visual system. I've exaggerated the length of the tail. Now look at that black quadrant, and the average of its spatial position is shown as the red spot. So the green spot shows the actual position of the rotating target. The red spot is apparent position. Notice two things. First of all, the red spot trails behind the green spot. That doesn't matter. But secondly, it moves along inside through a smaller circle. So in other words, you get perceptual shrinkage of circular paths. I can show you that in practice. Here you see three spots. Now imagine those move all of a piece through orbits that just touch, as on the right. Well, now you can see those orbits look as though they almost touch, or maybe the orbits are almost too small to touch. But now you can see the orbits are much larger than you might think. They actually overlap considerably. So this shows we've really got rather large overlapping orbits here, but now they look as though they're much smaller. So this is an example of shrinkage of circular motion paths. Click, click. Okay, now on slide 39. So when we think what causes flash grab, on this first theory, we're suggesting that targets flashed at the turnaround points get sucked in towards the center of motion, because the motion of the square or the background wheel gets reduced in size, and the flash marks the turnaround points, which now look closer together. So you get a flash grab. That's the first theory. The second theory is a bit more sophisticated, and it's not ours. This is Johansson, 1950. Now he considered, suppose you have a driver of a train. The train's driving along, and the driver waves his hand up and down. Now that hand traces out a sine wave, which is horizontally extended in space. Here's a rather crude diagram. There's the train puffing along to the right. The driver's on board waving his hand up and down, and you trace out that pink sine wave in space. But that's not what you see. What you perceive is a train chugging along and his hand moving vertically up and down. In other words, the train and the driver are perceptually grouped into a common horizontal motion. The hand is seen in vertical motion, which is a differential or relative motion. And our analogy here is that the, sorry, whoops, never mind. That's our theory. And here's further evidence. Johansson again showed that moving frames strongly affect organization and direction of motion, with his rather famous arching spot, which you can see, slide 43, appears to move along a series of arcs and then goes back again. It looks a bit like a bouncing ball, if you like. But now when it returns, we've added a central spot. Now it looks all the while like a rotating wheel, because you group together the common horizontal motion of the two spots, and you then see the differential motion of the two spots as a rotation, okay? Similarly, at the bottom of slide 43, one more click will show you, I hope, that when clouds move slowly to the left across a stationary moon, the moon seems to sail over to the right. This is Dunker's induced movement. It's just that our flash grab effect is maybe 10 times as strong. Okay. I'll show you now a rather silly flash item. You see here, I hope, a vertical, we're on slide 45. there's an oblique line, which I hope will jump up and down. I'll give it one more click. It's called a virtual Poggendorf. Okay, you see it jumping up and down. Now, when we put in a moving rectangle, the lines seem to be on either side of the rectangle and form a Poggendorf. Of course, they're not really on either side. They're really just placed one above the other. And I'm hoping by altering the vertical separation between those lines, we can measure the amount of the virtual Poggendorf illusion. Now let's look at peripheral vision, and in particular, how you see motion in the periphery. The first thing is that peripheral vision is insensitive to sudden transient motions. You're good at seeing smooth, slow movement, but any sudden jumps, the periphery just does not notice them. Here's a couple of demonstrations of that. We're now on slide 47. You'll see the top square is just jumping back and forth between two positions, and the bottom square is sliding to the right and snapping back, driven by a sawtooth. And that's what you see if you look straight at them. But now look away, and I think you'll see the top square appears just to flicker in place, and the bottom square appears to slide continuously to the right without snapping back. So in the periphery, you see the smooth motion, but not the sudden snap back. I've added the noise. It just seems to help the illusion on a bit. Okay? Here's a second demonstration of how the periphery is insensitive to sudden motion. Here we have two discs, and should start moving in a moment. Yes, there we go. Now, if we look straight at the top disc, you'll see it's jiggling around about a fixed average position, and so is the bottom one. But now look away at the edge of the screen, and now the two discs seem to be swimming apart like two demented tadpoles, getting as far apart as quickly as they can, even though, of course, they never swim off the screen. So here again, you see the outward smooth movements of each tadpole, but you do not see them jumping or snapping back. So this is one example of peripheral motion detection. The other one with which we want to conclude is an effect that we've called the furrow illusion. Let's look at that. So far, we've suggested in the flash grab effect that motion can constrain perceived position. In other words, a moving target can alter the perceived position of a flashing target. But now we're going to say that the position of a static background can constrain the motion of a moving target. And this only works in peripheral vision, we think, because of spatial averaging, as opposed to the temporal averaging that we talked about before. So let's look at examples of the furrow illusion. So I don't know what slide we're on now. Okay. Okay, you should see a set of oblique stripes. And on the right, you'll see a small gray spot moving up and down. Look straight at it, you can see it really is moving vertically. But now look on the left at that static red fixation spot, and it looks as though the gray spot is now moving obliquely parallel to the background stripes. Do you get that? What's happening? Well, it only works in the periphery, because when you look straight at it, you see it going straight up and down. So what's happening in peripheral motion to give you this weird illusion? Well, here's what we think is happening. I can't see my slide number. At the top, it should say furrow illusion direction. In the diagram, bottom right of the slide, you see a gray spot that's moving vertically upwards, as shown by the blue arrow. But as it moves, the terminators, or the ends of the grating, flow around the edges of the spot, and they move on average down to the left, like towards 8 o'clock. So the perceived direction which the spot moves is the vector sum of that upward blue arrow and the down left red arrows. So what you actually see is a spot moving up to the left in the direction of the green arrow, parallel to the background motion. Let's show you some more examples of that. Now, here we've taken some surgery to the grating. So on the left, the spots are moving along clear paths, and the gratings touch only the sides of the spot. So the terminators flow along the sides, flow vertically along the sides of the spot. On the right, we've trimmed away all except the path along which the red spots go, a bit like a lawnmower going along a strip of grass. And now, if you look carefully, the terminators are going to flow left and right at orthogonal to the motion. Now look at the fixation spot in the middle, and I think you'll find the spots on the left that really go up and down, what you see is what you get, no illusion. However, the spots on the right appear to go in at the top and out at the bottom, in at the top, out at the bottom, a bit like the two sides of a letter A. And if you now look closely at the gratings themselves, look straight at them, you can see the gratings do tilt inwards at the top and outwards at the bottom. So again, the terminator flow is driving this Fourier illusion. Now, one very interesting we don't understand is that the Fourier illusion can resist crowding. I'm sure you remember what crowding is in the periphery. Suppose you're trying to read a letter like an N. If it's on its own, you can read it. But if it's embedded in some exciting word like Juno, you can't read it because the letters J-U-O crowd out the letter N. Now, what we find here is that the Fourier illusion can resist crowding. If you look straight at the spot, you see it flashes a few times and then goes up and down along the grating, okay? I don't know, it's jerking like that, okay? But if you now look at the star on the right, you'll notice two things. First of all, crowding means you can't tell the orientation of the strips of grating, and you cannot see what oriented grating the spot lies on. But when the spot moves, you can immediately see it does not appear to move vertically, it appears to move obliquely, almost as though it moves out of the strip on which it lies. And when it's moving down now, okay, if it's in peripheral vision, it should appear to move down to the right, okay? And now if you look straight at the grating it lies on, that grating slopes down to the right. Now it hops across, and now it moves down a spot to the left, and if you look at it in peripheral vision, you should see its motion going down to the left. In a moment. No. Okay, it should go soon. Okay, now it should appear to go down to the left, and if you look at the grating it's on, the grating lines do slope down to the left. So what's mysterious is the dot appears to follow an oblique path, even though we cannot report the orientation of the strip on which it moves. Now that suggests to me that motion can break crowding, that somehow we have one system for detecting crowding in static things, but that motion is a separate deal and obeys different rules for crowding. Now, the Fourier illusion can also distort shapes. Look at that circle, red circle, and when it starts to move down, up and down the grating, what you see is what you get. It's a good circular circle. But now look over at the right-hand star, and you'll see the points within the shape slide along intersections, distort the shape. They seem to ripple and go into funny, odd rectangular or elliptical shapes. So the Fourier illusion distorts the shape. Okay, I'll go on to the next slide. So I can't see the number of these slides. It's almost the last slide. Now here again, if you look straight at these dots, they appear to move around in a perfect circle, and they're completely independent of the background stripes. They don't make a slightest bit of difference. You see the motion perfectly. What you see is what you get. But now look over at the right-hand star, and now the motion changes dramatically. Instead of the spots moving in a circle, they seem to slide around elliptical pathways, like a vertical ellipse now and a horizontal ellipse now. So they follow a compromised path between their own actual circular motion and the orientation of the background stripes. So again, this is a distortion caused by the Fourier illusion. So our conclusions are that motion can shift position and vice versa. And now, do you see that winking eye there? Here's our last slide. She's winking at you. Now, really, the eye is staying just where it is, but it looks as though she is sliding back and forth and winking at you with her two eyes. Okay? Thank you very much. End of talk.
Thank you, Stuart.
Thank you.